So I think we can start. So the goal of today is to finish this static games of incomplete information. That is, we did it, but we haven't done the application part. This is the auction and double auction, which are the two permanent application of Bayesian Nash equilibrium. And after that, I think we will give some introduction to the dynamic games of incomplete information, and that will be all 8 chapters will be the basis of what we do for our one exam. I mean, you can tell me if you want to do a take home, or we can do it in the class. The exam will just take an hour, so I mean we still have class on that day because we lose some hour last week. So on the very last class, we still have class, and we only have 1 hour exam. I mean, that's the usual 1 hour exam. It's not something that we don't need very long, right? Because you don't know. So bumble. So bring whatever you need. That would be fine. Just remember, you also have to finish your project as well, right? So that are 2 things. So let me quickly review what we have been doing in the last class, all right? So I guess it is something maybe a little bit. It's 2 weeks again, so probably hopefully it shouldn't be too still remember. So basically the difference compare the static games of complete information, incomplete information is like the types, right? Where the types would include the incomplete information one person has, right? And also the type would tell you the payoff. So the type is a generic term that help us to include the idea of incomplete information, right? And we didn't mention it, but probably you would know from undergraduate economics, we know that information asymmetry would likely to kill the market. Look at the Lemon's problem. So that means that the thing that we learned in chapter 1 to chapter 4 doesn't apply very well because the market doesn't exist anymore, right? So that's why you need to design the market, right? So that's why the auction is there. Auction is the way that a auctioneer or the seller who want to sell the product, but he doesn't know how to sell it, right? Because you realize there's no market can be clear if he has to rely on competitive market, right? So that is the main idea, right? Because the market is going to be gone, right? There's no competitive price anymore. So he has to discover what the price should be, and he has to rely on auction. It's one way to do it. Of course, there may be another way to design a market. That's why there's a recent research in microeconomics would be what we call market design or mechanism design or economic design are the things that we do, right? That's actually what the stock market, right, is design problem, right? Or IPO is a design problem. Or in environmental, right, the carbon trading is also the carbon market is also the thing because the market doesn't exist to solve externality or incomplete information setup. So these are the things that actually where you would do things, right? And basically accounting, right, or finance is trying to solve the information asymmetry, right? Because that's what the accounting is doing is a verification of the financial information, right? And same as marketing, right? Marketing would be doing a similar procedure, right? Try to help the firm to get the information from the people, right? And then and look at how consumer, right, buy based on income information. These are the very important application, right? But do note that when you write a model, right, unless information is the main concern, so otherwise you don't really want to model it, right? There's a usually it's a informational friction, will not change the main argument. But if the information asymmetry is so severe, right, it can change a lot, right? Just like the Lemons model as you have seen. So just to go back to the idea, right? It's just with some sort of common belief, right? That is before the nature draws the type distribution, everyone had the same belief over that. And as a Bayesian means once I drawn my type by the nature, my belief over all the others follow a Bayesian approach, the Bayes rule update. So that means that if I know your type, okay, and I would have the same belief as you do, okay. Okay, so that is very important. Okay. And that means that there's no inconsistent belief. So the idea of Bayesian game, right, would be the same as before, except we have T and P here, right? T is a type, and P is a belief, okay? And do note that belief is PI is derived from the common prior. And we have the Bayesian Nash equilibrium, which means that for every type, right, you would choose a strategy such that the maximize payoff based on your belief. Okay. So, and we demonstrate example that how you would do a Carnot game with income information, and that's how you derive. Okay, so this is something that I hope you know how to do it, because this is something that the minimum requirement, right, for our course is to solve this kind of game, right? So to be able to solve this kind of game there. So an auction is one application that you can solve this kind of game, and we show you how to solve some of the model, okay, here in auction. And then last time we talked about there are 4 types of auction, right, in the literature that people often study. And this English auction and Dutch auction, right, is technically not a static game, because the game proceeds according to people action, okay? So you should actually follow the paradigm that we study later today. It's a dynamic game, but turn out that they have a strategic form, and they're so similar that, I mean, in the literature, they would consider to be first price auction and second price auction. But these days, and I think people realize that they're very different. And that means that say English auction, the dynamic nature is very important. Okay, and but that will be a technical point that make in the recent literature. So we will do the even simplest version, right? We focus on the 2 auction that studies people submit bid simultaneously. So that actually means that it fall in the static games of income information, right? But later you will see is able to understand they're actually different thing, and then there's some reason that why we use the sealed bid rather than the open auction where people keep doing things. But okay, there will be no difference when the value are private, okay? But the value are related, and this English auction and Dutch auction do make a difference, okay? But that would be because you would learn according to the game proceed, right? Because but in the independent value, you don't have learning, so that's why in the simplest setting, these 2 auction and these 2 auction will be mostly the same. But in the case where auction is a proceed accordingly, the information is learned along the way that the auction is being conducted. So that's why there's an equivalence between the two types. So that's why we focus on them. And as we said, we're focusing on the seal bid auction. So that's why we can model this game where there's a buyers and seller, and the seller basically is a design problem. So basically, we consider seller able to commit the type of the design what kind of rule, and once they decide the rule has a commitment power, such in a way that he designed the game and the game is over. It's just a sub-game perfect, the barrel induction idea, right? He designed the game, and after that, the player, actual player, the buyers, they would play according to the game, okay? And the seller is not allowed to change the rule of the game. That's the commitment power there. Okay, that's very important, and there's a lot of research go on to say what happens if things are different, right? And in this case, right, once they bid, they are don't allow resale, right? Don't allow a lot of stuff goes on there, right? But that would be the idea, okay? So that it's an allocation problem, right? That's what economics is about, right? There's a item that the seller has and want to allocate, send it to the buyers. Okay, and there are many framework that you can analyze, right? And then we focus on the most simplest one, the project value, where each buyer, potential buyer, the value the good is independent of each other. It's like art, antique, or things that you have your own consumption value. Okay, and it's not related to selling. Okay, if you consider common values, you can sell it again, then it will be something even more complicated. Or if interdependent value is like the oil drilling or an antique that you think of the resale value, then it's more complicated. Okay, so these are very complicated, and there's a active in the recent research. If you don't want to do research, that will be there, right? That rely on the private value. I mean, if you are from the finance or marketing, look at the stock market, the private value is not the best, right? The common value may be a good because you can always sell in the market a certain price. So common value may be good, or interdependent value if you allow each investor would have their own value of the stock, right? That might be also okay, but the common value approach will be one way to go. Okay, but again, we focus on the simplest case, and the model is very simple, right? Just assume there's one object, and the recent literature focus on many objects. You can do that. Okay, and there's no use of these objects, and it's a cosine linear utility, which means that the payoff except P with P is linear. Okay, I mean there's recent paper that's trying to drop these things. Okay, so these assumptions, everything can be relaxed, but we focus on the simplest case. And here we have a fixed number of bidders, and indeed there's a paper that talk about entry, right? Bidders can be different entry costs can be probabilistic, but we focus on fixed number of bidders, and valuation is different, right? Drawn from some distribution, and we assume this is a cosine linear. The payoff will be the VI minus P, right? It's linear in money, and this again is one of the major obstacle in mechanism design or economic design problem is you have a assumption on linearity, right? And this is the part that where actually recent research goes about. So these are the part that you can look at the recent literature and how you relax these assumptions. Okay, and the question on the auction would be how to allocate the object efficiently. Okay, that is the problem actually as a government, right? I mean, if the government try to sell something, that would be the things to do. And the second question, which is related but is a distinct one, which is asking if I want to maximize my profit, expected one, so what should be done? And do note that in particular in this case is you need not sell the object, okay? Because it may come to the guy that actually a very low value for all buyers, and then you don't want to sell it, okay? And if you set a reservation price where it's the price where you won't sell the object, in that case, and then that case will maximize your profit, okay? So that means that these two are not the same thing, okay? Efficiency and profit are two distinct goals, okay? So that's why sometimes, right, you can see government in Hong Kong, right, the land auction, don't always sell the land. If they think the people making the price is not high enough, they will not sell. Okay, so it's but if right, in this case, the seller has zero value, right? So it's always to allocate to any positive price, right? And then to the guy who want to pay most should do, right? But you can see that two distinct goals here. And as we said last class, if the seller knows exactly who want to pay what, then you just come out and then set the price that exactly as the highest willing to pay, and that's efficient, right? So this is the simplest model. Of course, we know it's not possible, right? So we have to resort to incomplete information, and where we would have assumed the auctioneer have commitment power, where auctioneer has to commit the allocation rule and payment rule. So these are two rules, which means that bidders would focus on making a bid, a number, okay? And he has to decide if make the bid and how much one have to pay, if he win or he doesn't win, right? I mean, because he can make the auction in such a way that everybody have to pay, regardless of win or lose. That is what we call all-pay auction, and that's what we often use in a lot of application, right? Just like, right, only say you write your paper, right? You want to publish in the top journal, right? Everyone pay effort to write a paper, but maybe only a few paper can end up in the top journal. So it's an auction, right? But everyone pay it only if the one who produced the best would get it. It's a context. It's a large literature on that. So a particular application of the auction, right, is you consider the rule that everyone has to pay, right? You allocate to the best guy, right? And there's a big literature on that. But we focus on the this particular case. Okay. So we argue that auction is a mechanism, right? It's the way there's a well-defined allocation rule and payment rule. And as you can see, the early literature focused on auction, which talking about allocating objects to people and with payment, right? And indeed, this is actually generalizable more than auction, right? Because you can imagine that's what mechanism design is about. It's about how a guy who don't know what to do, right? He can take different action, right? And he asks people to tell him what to do, right? It's a resource allocation problem. Need not be indivisible object to one guy, right? Because the outcome of auction is allocation of the object to one of the person and how people pay, right? The monetary transfer and allocate object, right? But it can generalize to many, many things, right? Such as when government decide whether to, say, build a hospital in some place and ask people to contribute to it, right? It's what we call public good provision problem, right? And there are many, many things that along this line can be generalized, right? Because basically the idea is someone wants to do something on behalf of some people, and you need some input from other people that they have potentially withheld information, right? That have designed it in a way such that it's efficient, right? Just same as the boss. It's organizational economics, right? The boss need to design a system so that makes sure everyone works, right? That's what the tenure system, right? The tenure system, right, is a system where you want your staff or your professor to work, right? So it's a concept theory, right? That is, we have time, we'll talk about that, right? So for those arrive late, we have an exam 2 weeks after, and at that class we talk about concept theory because exam only lasts for 1 hour. So at that class we also talk about some concept theory, which I'll upload this slide later. But that's the idea, right? So you can look at recent literature. Basically, it's a design problem, and that will connect to operation research idea, right? More recent is more about information design. Okay, instead of talking about how to design the mechanism, is how to design the information revelation. Okay, but that would be something we don't have time to talk about. But if you have time, we can talk about those. Okay, so here we have a simple mechanism design problem where the seller only commit to two different types of rule, is to tell who is going to get the object. Okay, And in auction, it's going to be the one with highest. Okay, this is the deterministic, but you can allow probabilistic like lottery, right? You can say who is going to win depends on lottery, right? And payment rule is specify who is going to pay what, right? Its first price is to pay the bid, second price pay the second highest bid. You can imagine third price auction and cave price auction, right? That is also doable. And here it's very simple because you have one object here, right? So it's very clear that what is first price, second price. But what about you are auctioning more than one object, right? Which often in the carbon trading or in IPO or in the treasury auction, you have more than one, then how you do design, right? Are you going to do uniform or discriminatory, right? Because you pay as their own bid, right? Second highest, or what are you going to do? But that would be something that more complicated. So focus on a case where you only have one object, okay? And the Bayesian game would be the type and the belief, okay? So as we said, we focus on the IPV, independent private value. So my value is independent of yours. And I know my own cannot help the others, okay? And we also focus on the symmetric idea is everything is symmetric, drawn from the same distribution. The reason we do that is just to derive formula, much easier to get intuition, okay? It's not necessary. If you don't have that, then the model become not tradable. You can have write down FOC condition for equilibrium, but you can't really go further. So that's assumption, okay? So I know my value, okay? If I value the object by $10, okay? My belief on your value will be the same as you have the same value as I do, okay? If I have $10, if you also $10, okay? My belief on you will be the same as you believe on me, okay? Conditional on your own type, the belief is the same, okay? And actually, regardless of my type, right? Because independent private value. If I think what the distribution of your value is independent of my value, no matter what way I draw, I would believe the same as what value you are. Okay, so that is the problem. And then to make it normalized, the value becomes 0 to 1. Okay. So the bidding strategy, okay, is remember you have to specify strategy for all possible types, right? Because it's a sub game, right? Where the nature decide what value you have. So you tell me that if you value the object at $0, what you bid. If you value the object by 2.5 cents, what you bid. If you value the object by 50 cents, what you bid. So that means that it's a function. Okay, that is the part that probably will be a little bit tricky to you, right? But that is same as what we said in subgame perfect equilibrium, right? Remember the Stackelberg game. Okay, if you are the follower, what is the strategy? Your strategy is give me what the leader produce. You produce what, right? So you give me it's a function, right? Depends on what the leader produce. You would do what, right? It's a function. So here the same. Okay, you would take the nature, what value it assigned to you. You would put a number, but you have to tell me for every value that nature picked for you, what number you're doing, right? So in fact, right, if each universe of you, okay, the nature decide what value you are, you only pick one number. But you have to specify for all possible universe, the nature might pick you. So that means that it's a function. Is that clear? This is very important. So it's not a number, but it's a function. The reason is, although in any scenario, you only pick one number to bid, but you have to tell me that for all possible cases, your valuation, it might be you pick a value, okay? So if you have the nature give you the valuation 0, what are you going to do? If nature give you 10 cents, what are you going to do? The nature give you 50 cents, what are you going to do? The nature tell you 1, what are you going to do? Each time you do one value, but tell me every possible value. So it's a function, okay? And remember, you cannot be non-negative, right? You cannot ask the bidder to pay you, the seller pay you money, right? And here is a definition. If you bid what you think, right? If you value VI, you bid what you get, 45-degree line, right? Then you're true bidding, right? You bid honestly, right? Of course, it might or may not be reasonable, depends on the rule that imposed by the auctioneer, but this is the idea. And these are two things that would be important. Overbid, okay? If you bid more than you value, then you overbid. If you bid below, you underbid, okay? And actually you can see, which I hinted to you, if you do second price auction, you will do the triple bidding, which I argue later. And if your first price auction, you will do underbid, okay? The reason is very simple, because you have to pay what you propose, all right, if you win. So that means that you don't want to bid truthfully, otherwise you don't have surplus. So you underbid. In the case you win, you have some surplus. And you may ask, when you overbid, okay? You overbid, okay, when you talk about third price auction, fourth price auction, fifth price auction. In that case, you will overbid, okay? So it's depend on the rule, okay? You can do, any of them can be optimal, okay? But we focus on first price auction, second price auction, so you can forget overbidding, okay? So especially in the independent profit value, right, model. And if you drop the independent profit value, say suppose they're correlated, right, then you may overbid, right, because my value is high, the other value also high, right? And that can be you bid more than you think, because your own value, not just this guy, maybe also depend on other people correlation, right? But anyway, just let me stop here. So this is the graph, right? So we try to argue that this is the case when we have a first price auction. So the payment rule is very simple, right? It just depend on, it's a function that maps from the bids from everyone to the rule, okay? And here is the cosigning payoff. If you win, you will have the valuation object minus the rule that assigned to you. It depends on how it determined, maybe second price or first price, right? If you lose, you get 0. Okay. So, and assume with neutrality, which greatly simplify the proof, okay? And expected value, right, is you win, you get the payoff, you lose, you get 0. So that means that your payoff will be how likely you win and how the surplus. So it means the following. If you're risk neutral, basically you care two things. Actually, the trade-off is how likely you win and the surplus you win, right? And you can easily see that if you bid more, you're more likely to win, but you have lower surplus. So basically, it's a balance of the two things. Okay, so you can see this is the part that make things easier. But if you don't have risk neutrality, that is a little bit different, right? There's another part goes on here, then it's not so simple there. But there's risk neutrality buys us a lot of mileage. Okay, and of course, that paper that generalize this to more general framework, but that is, we stick with very simple framework here. So let's argue the first price auction. Okay, let's set a setup, and then we argue that truthful bidding is a weakly dominant strategy. Okay, so second price auction, what is the game? The game is like, if you are the highest bidder, you win. Okay, and if equal, then we will just make the simplest case. If everyone, there are more than one guy that had the object is thrown away. That part, you don't have to worry about that, because we assume the value is continuously disputed. And in that case, this event will happen with 0 probability. So we just technical assumption there, we just assume. Or if that's the case, maybe the auctioneer could not go in to sell the object. That's fine. I mean, that can be done. But okay, and the payment rule is the following: if you lose, you don't pay anything, right? And if you win, you pay the second highest bid, right? The bid beside you, max out besides you, right? And as I said, right, if you do the all pay auction, that would be you pay your own bid regardless of what, right? But this is the game. So basically you change this, right? Then you have fun, right? Usually the allocation rule is always fixed, right? The one who bid the most will win. That's usually not a game you can change the allocation, but the payment rule can change, and then you can derive different property of the game. And the payoff will be just based on allocation rule and payment rule of this, right? If you are the only winner, then you get the payoff, right? If you are losing, you get zero. So this is the game. Okay, I hope it's clear, right? Everyone sent the bid, right? So let's argue that truthful bidding is a weakly dominant strategy. Okay, we'll try to argue that. Okay, and the first argument is looking at, of course, we'll try to do the proof in the upcoming slide. Okay, but let me give you the intuition behind the proof. Is very simple. It's a little bit tedious, but the proof is very simple. I'll do this proof because I think this is a rather interesting proof to do. It's very simple proof. Okay, so the idea is why truthful bidding is a weakly dominant strategy. Remember, weakly dominant means that this strategy would be no worse than other. It's a weak inequality. Right? Compare all the strategy. This strategy is always as good as the others. Okay, there's no strategy that can beat it. Okay, so there may exist another strategy as equal as well as this one in some scenario, but this scenario you can't find a strategy that's better than this one. Okay? So that means that we don't prove it, but you can see if something is weakly dominant, it will be a Bayes-Nash equilibrium, because this is the best no matter what your other people doing. Okay, no matter what information the other people have, then that will be the part of the Bayes-Nash equilibrium. Okay, so if you overbid, what happens is if you overbid and you win, right, then you will be paying things that you don't want to pay. Okay, and you will force to buy something at loss, so it doesn't worth the win, right? And you win at the wrong time, then you make a loss. Okay, and then you also compare underbidding. In the bidding, maybe you may have won, right? But the problem is there's a you won, you don't win the time you should have won. Okay, and we'll prove that part. Okay, so I will prove that there's a two type of strategy, and the true bidding works the best. Okay, so this is the idea. Okay, so let's consider the case. Okay, we consider scenario. Okay, we denote the B star minus I is the highest bid R than I. Okay, this is the first term. The second one is UI star will be the payoff that actually happen if you win in this case. Okay, so let me repeat. The first one will be the maximum bid by others. Okay, that is called the B minus I star. Okay, the second item will be if you actually win. Okay, if you happen to win this is UI star. Okay, so now let's see what happened. Now, the easiest case is look at this guy, the middle one first, 0, 0, 0, y, because if your valuation is same as the highest bid by others, okay, no matter you win or you lose, actually will be 0, right? Because if you lose, of course you get 0, right? If you win, then you also get 0 because you pay, right, as others, right? So no matter what you bid, get 0, right? Because you bid the same, you get nothing, right? So 0 there. Okay, so no matter what, then you get 0. Okay, now you see the other case. Okay, if your valuation is higher than others, right? So suppose everyone is bidding the maximum, others bidding $10. Okay, and your valuation is 15. Okay, so you're higher than others. What you will see? Okay, if you bid 15 as we said, right, you win, right, because other people at most is 10, right, and that means that you win and then you earn some profit because you value at 15 and the maximum is 10, right? So you earn surplus of 5, right? And if you bid higher than 15, you bid 20 100, you still win with the same margin of profit, right? The same payoff. But if you bid lower than 15, okay, you still win if you more than 10, right? If you less than 10, then of course you lose, right? So in this case, actually you don't gain anything by underbid, right? So that means that in this case, right, you would always better than underbidding, right? And look at here, okay? If other people are bidding $10 at most, right? So if you bid 10 or below, you don't win, right? But if you bid more than 10, right, and you will lose, right? Lucky. If you're lucky, you win, then you will actually get a negative surplus. Okay. So that means look at what you do in the middle, right? You do in the middle column. Middle column is the truthful strategy. Is no worse than no matter what you do in the other way around, right? So in this case, same as here, but can be better here, right? Look, this case is always 0. Look at this up and down, right? 0. This is negative, right? So that means that bidding, what you're supposed to do is weakly dominant, right? It's not strict because they're equal here, right? So that's not strict, but it's a weakly dominant strategy, and it can be shown, which we don't have time, but you can guess if every agent is doing a weakly dominant strategy, it will be a Nash equilibrium, right? Because it doesn't depend on your belief, right? In this model, right? There's no belief involved, right? So no matter what I think about others, it is the same, right? So that is regardless of what you think about others, right? So that means that this, no matter how update your belief, the same. Okay. So that means that we prove one thing, okay? There is a B.N.E there, right? But there can be more than one, but this is the, oh, wait, maybe I should write this A.B.N, but it's not there, it's A.B.N. Okay, because it depends on the scenario, then it can be more than one B.N. I cannot prove that. And now the next is about the first price auction. So the main difference of this guy, right, is that you pay what you set. Okay, so the only difference is this one, right? The first, same, you're the highest bidder, you win, you pay your own bid, right? You lose, you pay nothing. Okay, so the same thing except this guy. And again, the same, right? Is the expected utility will be the trade-off between how likely you win and the surplus you win, right? Because this is 0 as well. Okay. And obviously, by construction, you will never bid more than you want, right? Because you bid more than you want is always negative, right? So you always underbid, as I said, right? So you will never bid the truthful, right? Because bid truthfully, then you only get 0 payoff, right? If you bid underbid, there's some positive return. Okay, so only consider that part. Okay, and as I already said, the undershade bidding. Okay, so we first prove a much simpler result. Let's assume f is from 0 to 1. Okay, and we have closed form solution. If f is a general distribution, then we will have a solve a differential equation. Okay, but let's do the simplest thing first, and then because we're PhD level, right? So I think differential equations should not be something that we very much afraid. But let's focus on the case. Let's look at interpretation here. Look at this. What is the optimum bidding here? Okay, optimum bidding is a function, a constant function of your valuation, and which turn to be this constant function is n minus 1 over n. Right, so it depends on number of people, right? If you write that, it's 1 minus 1 over n, right? So that means that if n goes up, right, what happened? When n go to infinity, this become 1, right? And when n is 2, there's the best case. You only bid half of that, right? If n is 2, 3, 2/3, right? The more n, then you would more likely to beat the real one, right? So that in some sense, right? In the market is large, right? And it's super large, right? Then actually the first price auction and second price doesn't make a difference, right? Because you actually bid what you want, right? You don't really bid something other than that, right? You bid something very close to V anyway, right? But of course we have some margin because you also want to win with some surplus, right? We will not bid exactly the same, but we're very close to that, right? And the reason why is written N, right? The idea is you want to win, right? And you want to only bid at the price that just beat the other guy, right? And if more people there is symmetric, right? More likely that the other guy will be higher than you, right? The valuation, right? And but anyway, let's look at the proof and then you will see. Okay. In this particular case, it's what we call constant shading, which means that give me whatever value, you just bid a fraction of that. That makes the model pretty tractable. Okay. So that is the idea of the graph. Okay, the proof. Let me do the proof. I think that is something we can manage to prove that part. Okay. So what we do, because we only prove this is part of equilibrium, and that is standard proof when we talk about base-Nash equilibrium. Because there potentially, usually, you have many equilibria that's possible. So usually what we do in many cases, we assume linear equilibrium. That is the example there. We assume your strategy is a constant function of your valuation. Okay. It doesn't have to be auction, but many other cases will be something like that, the linear property. Or you can assume that quadratic polynomial also can be done. Okay. But in this case, linear, and you assume everyone do the symmetric case the same. But we will prove that is the idea like this. Okay. So what you do is you assume all the other agents are doing the same strategy. Okay, we focus on symmetric strategy. You assume other agents, other bidders are also following this alpha strategy, and you want to prove that. Okay, you also want to do the same. Okay, you have to prove the okay. Okay, let me state it because it's very important. Okay, you have to prove optimality in this way. You want to have a symmetric linear equilibrium. Okay, how do you prove that? First, you have to assume all the other agents, bidders, okay, are also employing linear strategy. And under that, your strategy also linear. Then this is equilibrium. Okay. You would allow you to, because other people doing linear, you may not do linear, right? You have to prove optimality first, then that will become a equilibrium. Is that clear? So that's a very important part. Okay. You cannot just assume everyone do linear and solve the equilibrium. No. Okay, you have to assume other people linear. And under that case, your optimal strategy is also linear. You don't restrict yourself linear. Okay. Restrict all other agents, they do linear. Okay. And then you follow that, you derive your utility, you derive your optimal strategy, turn out to be linear. And then you can say this equilibrium. Okay, that's very important. Okay. You cannot just assume equilibrium is linear, everyone do linear, then equilibrium, because linear is not restriction. Linear is only the restriction that everybody will do linear, I do linear is optimal, right? We are only restrict the equilibrium in this class. Okay. Linearity is not equilibrium concept. It's rather we focus on this simple, much more simpler set of equilibrium. Okay. You have to still show optimality. Okay. So that's why here we don't have alpha V. Okay. We only have alpha Vj because Bj is using Vj here. Okay. And then we reverse it. Okay. And because of we think others are uniform. Okay. That's how you get this guy. Okay. So let me do it. You win, right? Given the other bidder. Okay. Only if you win this one. So assume this is only two bidders. In this case, only two bidders, I and J, right? So you win only if you hire the others, right? Then you win with this money, right? And if you win, your bid higher than other people, but what hard people do? They will bid alpha of the VJ there, okay? And then you figure out that the probability will be this amount, okay? And then you have to choose the alpha to maximize this guy. Okay, you choose the B to maximize this guy. Okay, and this B will give me 1/2, right? Because forget about this, right? Square half of that, right? Half of the VI, and that tell me alpha is 1/2. Okay, don't note that this is independent of alpha. See, you differentiate this, right? You differentiate BI, choosing BI. This is the part where bid is independent of alpha. Okay, how much you bid is independent of probability of chewing, right? So that means that everyone will do half. Okay, because I derive it independent of the alpha, right? So I don't really rely on that. I don't need to solve the fixed point because independent. But anyway, no matter what alpha you do, I'll do half of my bid. Right? And here actually we can generalize it to more than two agents, two bidders. If n bidders, okay, this is a standard classical probability theory, right? You have to higher than all the others. That means that you have to higher than, suppose guy number I, you have to 1 up to n, but you accept yourself. So it's n minus 1 inequality here, right? And it's independent. That means that the n minus 1 inequality to be there, independent, right? And that means that the same would appear here, n minus 1. And you differentiate, you get this guy. So that means that do note that this is independent alpha. So regardless, as long as the other people using some linear strategy, okay? Actually, I can even allow this alpha to be different from different agent. Doesn't really matter anyway in this model, right? You can assume as long as the other people using fractional bidding, right? As long as this is true, that it will hold, right? And in the symmetric equilibrium, everyone bid this guy. Okay. So now this is the proof, okay? And indeed, okay, we actually can allow even more general proof, okay? Is we don't even allow linearity, okay? How to prove the general case is we go assume that everyone would bid same function is a beta function, okay? And of course, we have to make some assumption there. The beta is increasing in V, right? You have more, you value this object more, you bid more strictly increasing, and it's continuous, right? And I think this is the most, it's defensible. I think that is something like, it's okay, right? It's increasing defensible function, okay? And in that case, you can apply the same object, you get this guy, right? You can just apply that, right? Just there's no assumption imposed on that, except we assume some symmetry. So everyone will have this one. We focus on symmetric equilibrium. So that's how we do it, right? Assume symmetry. Everyone assume the same strategy there. And you take differentiation, okay? And we will use what we call inverse function theorem, okay? And I'm not going to go to the detail, but you can check because I think for PhD level, I think you can do differential equation, but it's not required, so I don't want to bother you with that. But actually, you can prove by this theorem, you can do the proof, and by fundamental calculus, you can end up with this guy. Okay? So what we have is, as long as your F is uniform, okay, the only symmetric equilibrium is this guy. So it's very general, right? So we don't actually even need to assume people using linear strategy, okay? But why I want to show you linear strategy is because very often the equilibrium is very complicated. We often have assume linearity to derive equilibrium. Okay. And here we show you that, of course, there's a lot of algebra, which I don't think. I mean, if you want to work on it, you can work on it. It's not difficult, but you can prove that actually that's there. Okay. And probably one of you may ask, what happens if it's not uniform? With same formula, very similar formula there, but you have some integration. Okay, because it depends on how the distribution looks like, but it still have some very nice property. Okay. So so if you're general, what you have is what you expect to be the maximum bid of others. That's optimal bid. Okay, just to go back. Okay, what is actually what is here? Why is 1 over n this case? Is actually you want to win, right? And how much you bid will depends on what you expect other people's maximum their bidding, right? Then you want to win. Okay, so that would be the idea. You don't win, right? But anyway, so this is the last slide before the break. Okay, so we have shown see one thing, right? Assume the payoff is uniform, right? Sorry, right? Is uniform distributed among all the bidders. Your triple bidding is your prediction, and under uniform distributed like this. Okay, and when your n goes up, then actually the seal bid actually get very low. Okay, and if n goes up, this one drops. Okay, so this is how this behave. And do I do anything optimal auction or that? Okay, I didn't, but you can imagine that this is all the bidding, but here I didn't tell you one thing, and this for the revenue, we didn't say it. For the you can actually check for the seller expected revenue from these two auctions with the same. You can calculate expected value. These two with the same. Okay, actually to the bidder, to the auctioneer, it doesn't really matter which one you do. Actually, there's a very famous we call revenue equivalence theorem proved by Roger Myerson. Okay, he proved that the same, and that will be the same if you care about that. Okay, and they actually didn't have time to talk, but you can check textbook or other things. What is optimal auction? Okay, and also what would be the auction that will be revenue maximizing auction. And we don't have time for that, but you can check the textbook or other technical slides, and that would be something that if you want to go into this direction, that will be very important. Okay, but we just tell you that how you can prove how do you construct Bayesian Nash equilibrium, right? Because we show that I guess many of you will not be doing this kind of differential equation, but more than that, this linear property that would be useful for your construction of equilibrium. Right? Very often, there's a model is so complicated, you can't really characterize the whole set of every possible Bayesian Nash equilibrium because that's too complicated. You will see when we do the double auction of the brain. But very often we focus on the case where people have a linear structure, right? Depend on the information, and in that case, we can easily pin down the equilibrium, and that's usually how you apply this kind of model in the practice. Okay, and you assume uniform distribution, and that would be something. Although some of you may don't like it, but very often this is the best we can do, right? I mean, of course, sometimes they will assume various type of special distribution to get closed sum formula, right? But otherwise, if you really rely on some theory result, then you have to make some assumption there. It's very hard to have a general thing. Okay, this unfortunate fact. But of course, if you're happy with simulation, happy with those, then you can do whatever you like, right? But if you want me solving by paper and pencil, yeah, uniform distribution, linear equilibrium is something that you have to go. Okay. After the break, okay, we will talk about double auction. Okay, it's the idea that auction, in the case, it's only one seller selling the product, one product to many possible buyers. Okay, and that means the seller has actually a lot of power to set what they want to do, right? To set the scheme, what's the first price auction, second price auction, what can be done, right? Which is many cases possible. It's a monopolist, right? But very often, it's double auction, right? You can imagine that where the buyer and seller, they can set the price, right? And there's some way that the price being decided, okay? And you can imagine that IPO is a standard auction. Stock market is a double auction, right? Because in the stock market, you name the price on the sale, the other guy wants to name the price on the buy, right? There's a clearinghouse, which is auction, which is a stock market that met two sides, right? That is what we call the double auction game, and this is well studied since 80s, and there's a lot of papers still studying that in the operation management and also in economic design. There's a lot of problem how this being done, because this is the platform, right? They facilitate buyer and seller, right? Can you imagine, right? That's what happened, how they want to fit in this model. So, but we will talk about it after break. Okay, let's resume at 1:40. Okay, let's have 15 minutes break. 对，所以看得到，对，对，做一下。argue 他们的钱啊，在这里做这个。下周16号那个时间段，我需要我就不叫什么。在其他地方对，挺好，不知道有空知道的。对，然后我现在就是想自己是，我看到，我想现在就是先考虑这个，对，先把这个预抓出来的，对，然后再用新起一张，再去大概。对，你上手你才知道。我也没想结果会这么死啊，可能是你多的，就是那一般是遇到这种面试的情况，就是有限制法，比如说跟他有差别，对对，这点不来一件事。我先总结一下，应该就是主要是是不是要是说他们的六次方面，要交上什么，比较大小的。又是嘛？回了，回了，回了。我们这个课是到会最后一节课20，大概多少？大概是啊whatever，
就是只要不是
就不定几的，大多少个？记得没有？黑工的话就可以起一点，但是每天都没什么差别。黑工一个去考试，一个在学校考，对，考了一个考验了。对，可能就给一个周末吧。我黑工也在给一个周末，没有就是也没问题。到现在也考虑了一下。哎，对，要不然的就是30号，我们31号跟1号点有2天可以来，这个周末里自己做，但是 take home 就难一点，第三。然后再这样考一点。
对啊，对啊，对啊。啊，对对，最简洁，最简单的。对，周末给你一个周末3天，你自己随便做多少做多少，难一点哦，提醒你们，因为太容易大家都满分的。
然后多难的高考考试可以带吃的还是干嘛？
对啊，对啊。So you can tell me whether you like me to take home or you want 1 hour in advance. It's fine. Take home you can decide if you want to do. Take home 稍微难一点点吧，你周末会做，你周末做就基本在这里做两个到3个小时。
一是take home 还是2是 take home？
A 是第一个选择呗，对吧？A 就是 take home 了，对吧？B 就是这个了。A 就是 take home，B 就是这个。你们去公开投票也可以，没错。不用 stupid auction，can do a open ascending auction。So you want take home, then you go for A. If you want in the class, you go for B. Okay. There's 1 hour, or you want to spend more time. A 就是 take home。哎，按错 ，sorry。sama. A is take home, B is B is in class, so B decide. Because take home I can ask more difficult questions. More. You really can see how to your choice. If you please do that, we can do more liberal. Yeah. So let's see if we want to take home or I still have So please fill in. We decide going to take home or there.
It seems like everyone want to do it in class. Oh no, it's even. No. Why you can keep changing? Swing state? Who is 摇摆中? One more. One more. A take home, B in class. Okay. It seems like I don't need to wait. No. Last 1 minute, then I'm going to end. 再少一下。41617. 41617. Now, if you want to take home, then okay. Is it someone cheating? 有人在关票的。We have actually 18 or 19 students in the class, so that is not more than what's supposed to be. If we have 19, then I have to ask the vote again, right? Check the votes. 对啊 ，no voting ID. There, you whoever you pick. So is there anyone who is not picking? No? Then it's okay, we take home, right? If that is okay, take home. So it will be slightly more difficult, but not too much difficult. Okay. It's slightly, huh? It's A, right? So we just end. Otherwise, we never cannot continue the class, right? That's okay. Then I just take home. Is it done? Maybe I should set the time. Nhớ bài của anh nhiều. Okay. Okay, we have a class exam. So you will be you'll be easier one. Okay. So you expect to see something like the example we mentioned in the class, right? So you're able to solve those. So like maybe like how to solve the Carnot game with incomplete formation, how to solve this game, like the assignment what we have done, or the example we have done in the class. Okay, so you'll be something like that. Okay. So probably an hour. Probably you ask you just a few questions there. Okay. So don't worry about it. I mean, I will make more questions than you can answer. So you are not expect to finish the whole thing. Okay, so it's a relative ranking. So I see how well you're doing, and also it's a PhD level, right? So yeah, so that doesn't really matter anyway. And then we have a small class, so don't worry about the grade. I think everyone will be happy with the grade at the end. You may not be super happy, but everyone should be very happy with the grade. Okay. But anyway, grade is more or less useless anyway at your level, right? So I mean, no one care about your grade, and no one asked me my grade anyway. So you just only need to pass and write your own paper, right? So And that should not be an issue for you. I mean, just want to make sure that at least you know how to solve the game, and then you can apply what we learned, right? So hopefully that would be something that would be okay. So I guess we can continue with a game that is actually well studied in the literature, and they say it's also very complicated. You would think this is so easy, but why it's so tricky? Okay, so this is as I said, it's very similar to the idea in the stock market, and that's why in the finance literature, many of the time they consider this is the model that is in the stock market. So in this case, it's the buyer and seller, and they have valuation. Okay, so it means that the buyer want to buy things from seller, right? Seller has something to sell, and there were more than one seller there, right? So then the buyer and seller we decide what they need, but in this case we only have one buyer, one seller case. Okay, and they have a uniform distribution of value, and of course they don't know the other guy, they know their own. Okay, and the private value. So how much the buyer value the object the seller has doesn't imply anything about the seller, how he value the object. Okay, and by construction, it's possible there's no trade would happen, right? Because the seller may value the object higher than the value that the buyer has, right? So it's possible there's no trade. Okay, that's possible. And what is the strategy here? Okay, the strategy here is the following. Okay, so the game will be the following: is the seller simultaneously with buyer, they will tell us each other what price they want to buy and sell. Okay, and if the buyer is willing to pay more than the seller will willing to accept, then they will the strike price will be middle. Okay, and middle, you can imagine there's bargaining happen. So you can imagine one guy say 10, the other guy say 5, and they strike at 7.5. Okay, somewhere in the middle is fine, doesn't really matter anyway. So there will be some split or surplus. Actually, it doesn't really matter how they split. Okay, you can need not be 1/2, but the result will be very similar. Okay, and otherwise, if the price is not compatible, there's no trade. And the payoff is very simple, right? If you buy, right, you get the valuation minus the price, right? The seller will be the price minus the valuation, right? And if no trade, it's 0. Okay, this very simple game, right? And now here comes the what's the base and Nash equilibrium? Okay, in this model. Okay, and do note that there types for the buyer and seller is both side asymmetry. Okay, so that means that the buyer, okay, for every valuation he has to choose a price. So it's a function. Okay, so that's why the P of B is a price he not to name, depend on his valuation. Okay? U of B here is a little bit more complicated. Okay, will be his valuation minus, okay, his price, his name, plus the other guy, the seller's price, right? The seller price have to be the buyer must find the seller in order for this to work, right? And times the probability of win, right? So basically it's just previous case, right? If he wins, right, his price higher than other guy's price, okay, he wins, or sorry, there's a compatible, right? The trade happened. And trade happened, what happened is this valuation, this is a strike price. The strike price will be the price he named and the price that the guy named, but the price that the guy named will be an expectation. Right? So that would be that. The other guy, the seller, be this one. So the very difficult part is this guy, right? This is, we can see in auction already, right? The only difficult part is the price, right? This is different from the auction, right? Auction is you forget about the two, forget about this guy because you pay what you bid, right? But now this other part, right? How much you're paying not only depend on you, but also depend on other guys, right? So that is the part that's very complicated, right? You can see because this is depend on what you think the other guy would bid. All right, so this is very, very different, right? How much the other guy, this say the buyer, would think how much what a strategy of seller, right, would affect my bidding strategy, right? Because what the PS looks like will affect the surplus. Okay, so that will become very complicated, the model. Okay, this is same for the seller. So here, I mean, we can show that there's a many possible equilibrium. Okay, and in the literature, they would divide it into two different classes, but of course there are more than the two classes, but these two classes we can handle in our slides, but you can imagine they're more complicated. Okay, the first one is single price, which means that regardless of your type, okay, you will just do single price. And linear equilibrium means that your price will change linearly with your valuation. Okay, let's see what do we have. Okay, so what is single price is the equilibrium actually is more than one continuum. What is said is, okay, and any price is a Bayes-Nash equilibrium in the sense that the following. Okay, fix a number x, say x is 50 cents. Okay, say, but any number would do. Then a buyer would always, okay, if his valuation is more than 50 cents, he always only offer 50 cents. Okay, otherwise you got 0. Okay, so that's a strategy. So as long as we have a number, say 50 cents, and he value the object more than 50 cents, he will offer 50 cents. Otherwise, he would offer 0. And the seller does the same. If you value the object more than 50 cents, so the buyer, if he value more than 50 cents, he will say 50 cents. If it's below 50 cents, he will got 0. So that maybe I can draw a picture, right? So the strategy of the buyer will like this. This is the V of the B, which is the P of the B. So this X is here. So what we will do is, if valuation is more than X, we have 45-degree line here. Maybe other color. Okay. This 45-degree line. Okay. So what you will do is, the black color, if valuation is more than X, it will be just X. This is X, right? So he will be this line here. Otherwise, it's 0. This is the P of B, right? So whenever more than that, he will be this one. Okay, is that clear? What the rule is there's a number that both agree. If my valuation as a buyer more than this, I bid just the floor is X. Otherwise, I bid 0. I will not bid anything. And there is another one that is the seller. Maybe I use the color green, right? The idea is, if my valuation to the object is less than X, okay, then I will sell X. Okay. Otherwise, I will sell at 1. Okay. And you can see, right? So this is the model. Okay, this is the model. Okay. So when the trade will occur, right, it's only if this price higher than that, right? And as long as this X is in between the valuation, it works, right? So suppose 50 cents, right? If the buyer value more than 50 cents, then he will make 50 cents, right? If the seller is below 50 cents, then he will willing to sell at 50 cents. So 50 cents is the trade. Okay, the trade occur within this range. Is that clear? So you can make X a number, then you can imagine what's going on. Okay, so this is the Bayes-Nash equilibrium. Why? Because buyer cannot do anything to improve his situation. If the seller say this is the X is the price I want to sell, right? Otherwise I don't sell, right? Then what you do is only if your valuation higher than X, then you buy, right? Right? Then you reverse look at seller. If buyer use this strategy, you cannot do better than that, right? So that is, and this apply for any X, okay? So that is only this equilibrium, right? So this equilibrium is very not so funny, right? Because this is something like, okay, it's like for theorem, whatever is fine, right? So you can't fix you can't say anything, right? You can't explain anything, right? This is something that is yes, but this simple equilibrium, something that actually you don't like, because this is something stupid, right? I don't think people would do it, right? Just like your strategy is actually independent of your value in some sense, only a fractional idea, right? So is it not? It's not that you have higher value, we bid higher, right? So usually if we require that your strategy is monotonic in some region, then this breaks, right? We need to have some more interesting equilibrium, right? So the interesting equilibrium is what we call linear equilibrium, right? Where we would require the price that the buyer going to offer should be increasing in your valuation, right? So the beta B and the beta S, right? The beta B will be increasing, right? And the beta S also increasing, right? Because the price they are asking should be increasing in the valuation, right? So that is something related. But alpha and alpha can be negative. But anyway, that would be the idea. Okay. And here, as I said, if you have to assume linear, that has to be, we have to prove the following. First, you have to prove that first, if the other guy is linear, you also want to do linear. Okay. Then then there will be linear equilibrium. Okay. Do note that this is very important part. Don't miss it out. Okay. You can't assume they do linear and solve equilibrium. That's wrong. Okay. You cannot assume say, what happens if I'm linear, you're linear, what's the equilibrium outcome? No, that is not equilibrium. A linear equilibrium is saying that everyone follow equilibrium is optimal. Okay. When you check deviation, you have to check deviation that is not linear. Okay. So that's why the proof is the case. Okay. Linear is not a restriction on equilibrium definition. It's saying that we only look at this class of equilibrium. Does it make sense? It's not a refinement of equilibrium. It's only look at a subset of equilibrium that has follow some mathematical structure. It's not a refinement equilibrium. Okay. So that means that what we're doing is, if other people do linear, I can do many things, but turn out to be linear is optimal. Okay, that is very important. Don't make a mistake. Otherwise, I think when I was first learned, I make a lot of mistake on this one. So have to be very careful. Linear is not a big restriction. We only restrict we have many equilibrium. We only focus on the equilibrium that is linear. Okay, it's not a restriction on the equilibrium definition. Okay, there are many possible equilibrium, but we focus on the thing that's linear. So that is very important. Okay? So how to prove that? I don't want to bother with that, but I just want to highlight how we prove it. Okay. So here is the idea, but I think at pixel level you can read it. But the main thing is, maybe I just show this proof. The one about the optimal for the seller, I don't want to. You can do it by yourself. Okay. But let me go over this proof. Okay. This part of the proof. So your valuation is from 0 to 1. Okay. If the seller follow a linear, okay, then his price will follow this uniform along this one, right? Just the property of uniform. Okay. If you uniform, a linear transformation is still uniform, right? If 0 to 1. And if the other guy is bidding according to this, the bidding is also uniform, right? So that's the first thing. You can prove the probability theory. Okay. So now that means that this is the payoff for the buyer, right? We have said that. Okay. And what you do is replace this guy here, right? It's uniform, right? Uniform, it just the expected value is the highest minus lowest and over 2, right? That's why this guy, okay? This conditional probability, okay? You can actually prove that it's not something complicated. And then you can simplify into this one, right? You can, of course, you find this PB and turn out it's linear in your valuation plus some constant. Do note that this constant depends on the seller strategy. So which is different from auction, right? Auction, you don't have this part, right? It just depends on your valuation, but it depends on others. So then this becomes a fixed point idea. So you have to look at what other people are doing. Okay. So there's a proof of why I have conditional probability. That's how we get this one, right? Because I said you would do this guy. How do this guy here? This guy come from this proof here. Okay, and I'm not going to bother with the proof because I guess unless you are really doing this, it's not something that you would do, right? So you can do the same. Okay, you can prove that the same proof here. Actually, the same proof. I don't want to bother with that, but the price of the seller is also linear in the seller, and it depends on the buyer's behavior. Okay. Okay, so that would be the two part, right? There's optimal response. Okay, is this guy. What does that mean? Okay, how do you solve this? Right, we have two batch response, so we will solve this system. Okay, and we hypothesize this is the outcome. So we will do the math of what we call comparing indeterminate, undetermined coefficients. Right, there's a very standard approach, right? You look at that alpha B will be this 2/3, right? Beta B will be 1/3, right? And once you do that, alpha S is 1/2/3, and you know this guy already, right? So just put that in there. So you got the outcome there, right? So basically, you would beat 2/3 of your value, right? And plus some constant there, right? So here in this particular model, you will see it's not efficient, right? Because trade only occurs when the buyer value is more than a quarter of the seller's value, right? Because the best efficient case is this should be 0, right? You should only, because whenever this is a trade, right? And this 1/4 is the information fraction, right? Because of I don't know your value, you don't know my value, and that's no trade, right? So that is a part that where the efficiency, and that is the paper that try to talk about how to reduce this guy. Okay, but that would be a lot of research goes on, and then as I told you, this is a big research topic about double auction. Okay, but I just tell you there's something behind that you know what we can do. Okay, and the math I think it's okay. I mean, if you want, I can go back to the proof if you want to, but I guess here that's algebra, right? And this is uniform. You can do that, right? And that I don't think you need me to explain, but you can check the proof there as everything is very I think it's very the part is I think it's not something complicated. Okay, so this is very often appear in many cases because in confirmation is very often, right? When you talk about business, right? Especially finance, marketing, or accounting, or operation management, or environmental protection is also there, right? You consider there's a carbon trading, and there's a lot of things goes on there, right? When the idea why you need market mechanism design, right? It's because if you let the market to play around themselves, there's inefficient, right? So that means that there's a room for people to do things, right? As a designer, you can design the game so that there is possible to make this as small as possible. Okay, and actually that's what happened, right? And right, is that okay? So there's no problem. I hope I can go to the dynamic games because right, because I want to cover the topic 8 as fast as possible. Then you can start prepare your exam if you want to, right? I think. So what did we vote? I forgot. Take home in class, right? 1 hour in class. Okay, in class. Okay. So we're in class exam 1 hour. So don't worry, because 1 hour it would be very simple. So last topic, not last topic, but last topic that we've been exam. But after that, we'll talk about contract theory, and if time we'll talk about bargaining. We'll talk about contracts, more interesting stuff, because these are by itself is very interesting, right? But looking at the principle is not something fun enough, right? Look at application is more fun. So here comes to the most complicated game. We have dynamics, and you also have income information. And there's some way you can solve the equilibrium, which we call perfect Bayesian equilibrium. And you will see this is an extension of subgame perfection and Bayesian-Nash equilibrium. But there is a lot of complication goes on. One of the main reasons why is the dynamics. And the thing is how you do in the earlier stage might reveal the private information. That means the information not static. Okay, what you do may carry information signal, and that means that how people learn and update would be part of the model, and it has to be part of the strategy how people learn. And that means that compared to the past 3 topics, how you would think it work is part of the strategy, and you will try to manipulate them. Okay, and that's why we call PUA, right? PA is this is the PA, right? Is how you manipulate, right? The other partner, right? And that is very important. And as we said, right, information design is very important application these days in microeconomic theory, right? It's because of how if you are able to commit what you learn, you don't learn, right? That is very important, right? And and we will learn very important game. One of the important games is the signaling game. This is probably if you learn any Bayesian-Nash equilibrium, that's one of the most important application. And once you learn that, you master that, then you know how to solve all these other games. And do note that this game is super complicated to analyze. Okay, even the simplest signaling game has so complicated thing that we only touch the surface. And you will see, I mean, at least there will be three class of the solution. And the problem is there are too many solutions. Okay, as we can see in the static world. So dynamic world is even more complicated. So there's too many solutions. So the problem will become how do we pick the solution that we think that is most plausible. Okay, so it become a question. And luckily there's some refinement of the equilibrium that we think that will be more plausible than others. But let's talk about that in more detail. Okay. So as you said, there's a extensive form Bayesian game. And the problem is what you do in earlier round can be reflecting your information. Okay. And it can be informative, also can be misleading. Right. And the belief is no longer static, right? So it depends on what has been done. Okay. And whether I want to update. And turn out this is a very important thing actually for economists. They took like 10 to 15 years to understand that actually belief should be part of the equilibrium. Before they don't understand that. Okay. But after a lot of discussion, turn out that they would believe is actually part of the equilibrium. Okay, it was not thought important. Okay, for the static game or of confirmation, right? It turned out that this is very important, and solution has to join me, tell me the strategy and what are the belief, how people learn, update, right? Probably not surprising because many of you know machine learning, right? How people learning is very important. So it's not surprising, right? It depends on how people learn, if they're stupid or smart, or how you update is very important, right? And now you can see we have much more complicated thing here, especially we have this I is the single most important thing, right? And is self player, X is history, this is excessive quant, right? A is self action, player partition, okay? And P is important, is probability of nature, okay? And this is the part that where information asymmetry goes, right? Before you don't have P, and the I and the U are the same, okay? Of course, as I said, when you have dynamic games, no one actually defined this way, okay? But this is the way that you keep in your mind when you write your model. To make sure that everything can be found in your verbal description, okay? So that's why it's very important to learn the formality. It's not you have to write in this form, but when you write your paper, check everything is there, okay? At least people can understand what's going on. Otherwise, the game is not well defined. So first, probably as a good example, you will see before the break is why subgame perfect is not a good solution concept here. And do remember that subgame in this game only have one subgame because you cannot cut here, right? It's not a complete game, okay? There's only one subgame, whole game, okay? So the next equilibrium will be the subgame perfect because there's nothing to perfect. So now look at this one. What would be the Nash equilibrium, right? Nash equilibrium is subgame perfect. And look at the following. As I argue, L prime, okay, is a Nash equilibrium. Okay, look at L prime. Player 1 choose L, player 2 choose L prime. So the outcome will be 2-1. All right. So now look at, we want to check if this is Nash equilibrium. We check what? If player 1 want to deviate and player 2 want to deviate. Okay. If player 1 deviate, okay. If player 1 choose not L, go to M, what will you see? If M, it will be 0. Right? So there's not profitable deviation. Look at L, B.B. to R, 0, 2 to 1, not profitable. Right? So player 1 don't want to deviate. Right? Because 2 is very best compared to 0 and 1. Now look at player 2. Given player 1 choose L, if player 2 choose R instead of L prime, become R prime, right? He'll get 0. 1 or 0 must be 1. Okay. So do note that player 2 dash means that actually he don't know where he is, right? So he actually don't know whether LM is being chosen. Okay. That means that now we see that L prime and R prime is Nash equilibrium. Okay. And you can tell me which one. Oh no, I didn't check RR prime. Okay, I checked this one already. Now explain this RR prime is a Nash equilibrium as well. So R prime, the outcome will be just this guy, right? Because end of the world, 1, 3. So want to check if this is Nash equilibrium. Okay, if player 1 don't do R, he do L, he will get 0. Right? If you do M, also get 0. So 1 better than 0, player 1 not deviate. Player 2 is getting 3 here. Okay, but he can't do deviate. No matter L and R prime, the same. So it's 3. Okay. So these two are Nash equilibrium. Okay, but economists, the famous example, this famous example, and then we say this R prime is not plausible. Why? Look at player 2. Choosing L prime in this scenario is 1, this is 0. Right? L prime is greater than R prime. Look at this case. L prime is 2, R prime is 1. So player 2 is doing a strictly dominated strategy, right? If you ask, close your eye, you're player 2, what are you going to do? Always do L prime, right? That's no brainer, right? Because no matter what happened, L prime is better than R prime, right? So it must be the case that it can't be this is reasonable because you're assuming R prime is being chosen, but you shouldn't be chosen at all because 2 is better than 1, 1 is better than 0, right? So that's if he's reasonable, right? What you say is very important is he can tell himself where he is, right? He'll assign belief. He should be either here or some probability over there. Okay, and then when he, no matter where he believes, no matter what his belief can be, there's no way he will choose R prime over L prime. So that means that equilibrium only with strategy is not enough. We have to make player 2. You have to make a decision where you are and calculate your belief. Okay, because in this case, we actually think why this survive because he thinks he's here. He don't have to make the choice. Although this is something stupid, right? But he actually not here. Right? And that's why he's here because no matter what he do in the next equilibrium, he don't have to choose things here. So although this is stupid, but it can be there. Right? So that's a reason we don't allow them this happen. We have to make him or her to make some real decision here. Right? So that is very important. That's a belief is introduced in the system. Okay. Later you will see he has to decide where he is with some belief. Okay. So that is a very important part of the base Nash equilibrium. Okay. Which let me not talk about this before break because I think that's very important. Okay. So actually the perfect Bayesian equilibrium will be have a 3 requirement. Okay. First, it's very simple. When the information set, you have to assign probability where you are. Okay. The minimum requirement is probability, right? So in that case, it's maybe 1/2 is there, 1/2 there, or 0, 1, 1, 0, any number is fine. Okay. You have to take your sign. You cannot say I have all 0 there, right? In the previous case, it's all 0, right? You think you are there, you don't have to make a decision. The second is what we call sequential rationality, which means that according to your belief, you have to do something optimally. Okay. So this is the sequential rationality. Okay. You tell me your belief. Okay. But your belief have to be useful, right? Have to be the real belief, means that you decide according to your belief. The third one, so far we say belief is anything. But here now the belief have to follow Bayesian updating. That's come from the Bayesian equilibrium. In the sense that on the equilibrium path, what does that mean? It means the following. In this case, L prime. Okay, this equilibrium, L prime. Then it must be the case that 2 have to believe him he's here. Probability 1 must be assigned here. 0 will be here. What does that mean? It means that if this game is paying 1 billion times, okay, 1 billion times, what he learned, if they play another game, probability 1 will be here, 0 will be. Is that clear? So because this game keep playing, you ask him the next time 1 billion times after where he is. He should obviously 1 is L, right? 0 the other way, right? So that is called his beliefs should not be inconsistent with the game being played. Suppose this game played many, many times. So that is called the perfect Bayesian equilibrium, PBE. Okay, so that would be the equilibrium that is mainly used in this literature. Of course, a technical note, if you look at Masco, Winston Green, they will talk about another equilibrium we call sequential equilibrium, which is slightly more complicated one. But it requires sequence idea, but I don't want to talk about that. It's more technical. But okay. But let me say, in a game that you would work on, in application, the sequential equilibrium and perfect Bayesian equilibrium are equivalent. Only if some special game that they were different. So I think in most applications, when you do business well, they're the same thing. But when you see sequential equilibrium, more or less you can draw an equality line. They're very similar, almost the same. I mean, you can, there's a paper that show the equivalent in certain type of game, and this whole in general. But there's some special type of game that they're not equivalent. But they can more or less the same, okay? Unless they were talking about some special thing. Okay. So just to remind before the break, okay? A perfect Bayesian equilibrium has 2 things. Strategy profile, as we have seen already, but you have to specify the system of belief, which means that we have to assign probability to all information set. Okay, and as you can see, the equilibrium concept is way more complicated, right? And then means that you have to tell how people learn, right? Of course, we restrict to Bayesian learning, right? If you learn machine learning, there's a Bayesian learning, but how we learn, right? It can be very different, right? Because we only require learning on the equilibrium path, right? Which we ask them to play many, many times. Then you learn from the equilibrium, right? But off the equilibrium, if thing is not encountered, we can't say anything, right? So later you will see this is still leave a lot of room that many equilibriums, okay? But anyway, after the break, we'll talk about this example, and then we talk about the signaling game. Then you will see a lot of fun goes on. I mean, that will be actually very complicated. Okay, so prepare yourself. This will become the most complicated part in our course because I think it's the most complicated one. Okay, and it took me a long time to master this thing. So probably you may find it very easy, but it took me quite a while. Comparatively more difficult. But anyway, let's have a break of 15 minutes and we'll see you soon.
话都写过，所以你不一定可以达到非常的。哦，还有这个块，这说了，这块地点，还有 divine 块地点，差不多，和你回去跟这块地点，还有什么 all 比较高的三个，所以无限多的，无限多。对。他们是让你保持。来，确实有点，确实。 So hope you're ready for more complicated, most complicated part of our course. That is part of the exam.
So as we said, the perfect Bayesian equilibrium would require us to have two things: your strategy, but also your belief. Okay, so you have to assign probability over these two nodes. Okay, and you can assign whatever, okay, as long as you satisfy the three criteria. Okay, and R prime is not P because when you assign any probability, no matter how you assign, there's no way that you would say you would do R prime over L prime, because look at this, is you use this, right? Your payoff is as player 2 with P times 1 and 1 minus P times 2, right? And compared to the case when you shoot out, this is the case, right? And you can easily, by construction, this inequality is impossible. Okay, so as long as you are restricted to this, then you can't, right? Because you don't have to worry about this in natural equilibrium because you assign 0 to these two, right? So actually you don't have to worry, right? Actually you don't have to make a decision, but now you have to make a decision, right? Then you're forced to not say this is a PNP. And LL prime, and we'll say is a Bayesian-Nash to a private Bayesian, to PBE, sorry, so be PBE. And because this is chosen, okay, this must be 1, right? The reason you can imagine this game played many, many times, right? Always LL prime. It must be the case when you play the next time, P must be 1. Right? And P must be 1, and we'll argue that if P belief is here, it must be the case 2 is being chosen, right? Because L prime is chosen because compared to 2 versus 0. Okay, so that is the only belief. So we have a unique, perfect Bayesian equilibrium in this one. Okay, P cannot be arbitrary. Okay, so there's, although as I said, there are many possible cases. Actually, this refinement only left us only equilibrium that is perfect Bayesian equilibrium. So the typo is PBE. Is that okay? If that's okay, then we can show you a very famous example, which is called the signaling game. And then, of course, in this literature, there are many, many games, but same as the personal dynamic in the game, signaling game is a game that is so simple, everyone use it. And it's so simple because it is the case where the first guy who move first, second guy move later. There's 2 guys only, 2 players, first guy, second guy, and only the first guy has private information. Okay, so the first guy move has information. That means that how the first guy move, okay, can carry information then update belief, right? Because if reversely, right, if the second guy only has private information, then actually the game is very simple. Right? There's no learning going on, just standard Bayesian-Nash equilibrium, right? There's no difference. But now the problem is the first guy, how he moves, actually will reveal certain kind of information. Okay, and that can help us to understand what's going on. So the game is defined as following: the sender receiver, okay, the message is going to send, okay, is action to take, okay, and this type, this is the probability partition, this Pyra, sorry, and this payoff there, okay. So let's look at the game. The game will draw the type of sender, right? Sender, you can imagine they say good or bad, strong or weak, right? And then it can affect the payoff of everyone, right? And the sender first learn a type, right? And then he send the signal, okay? And the message is M, right? And the receiver would choose look at the message and update to the action, okay? So basically, the sender is, for each type, we choose one message. Okay, so it means that the sender strategy is a function of his type, right? For each type, he send a message, and the receiver, looking at the message, will take an action. That means that the receiver will have a belief, right? And depend on the message you send, right? And then if this message is sent, then he will believe what type of the sender is, and with the action. Okay, so it's a function that based on the message, right? And the belief is based on, and also a set of belief. Okay, depend on the message then. Okay, and the utility like this. Okay, it's very abstract. So let's focus on the most simple case. Is you have sender and receiver, and there are two messages the sender can send, there are two actions the receiver can take. So how to look at this graph is like a spider. How do we read that? The easiest way to read the center nature. Okay, center dot is here the nature, and the nature can go up or down with complementary probability, either type 1 or type 2, right? It's usually half and half, right? But depends. And the nature tell whether you are high type or low type. And the nature will go, the sender will decide M1 or M2, go left or right. So the sender decide left or right. Okay. But the receiver doesn't know he's actually the world is up or down. He just know whether he's left or right, right? He will just know the message M1 or M2. Okay. The receiver doesn't know it's up or down. Okay. The nature decide up or down. Okay. And the sender decide left or right. So the receiver only know left or right he's doing, but he don't know up or down. Okay. But up on the message, left or right, he decide A1 or A2. Okay. But he can't choose which one, right? He just A1, A2. Okay. So let's repeat. It's a very simple game. It's two type. The sender can do two type, up or down, T1, T2, right? And he can send a message M1 or M2. Okay. And the receiver can only do A1, A2. So what makes difficult is the belief. Okay. Upon seeing M1, what is the belief on type 1, type 2, and okay, M2, what is type 1 or type 2? So this is the most complicated one. Okay. And let's look at the example here. Remember, the perfect Bayesian equilibrium have three requirements. First requirement with system of belief, which said for every information set, you have to assign belief here. Look at that is, it must be the case that in this case, this plus this must be 1, and this plus this, that's it. First requirement must be probability, right? Just this guy, just make it clear. This and this must be 1, right? And same as the other side, okay? Second requirement is sequential rational, which means that what they're doing would be the best. Okay. So what does that mean is the sender will send a message. If you send left, okay, he will not deviate to right, given the action going to be taken by the receiver, right? Receiver response is give the message what he is doing. Okay. So given the receiver optimal choice, okay, then it doesn't depend on the belief. Okay, here it just depends on action. That is what required. Okay, and the receiver is slightly more complicated. Okay, so the typo here, this should be go down. It's part of that. But receiver is have to be the case is just a type. This typo only here. Receiver is based on his belief. Okay? His action is maximizing expected payoff. Okay, so don't worry, it will be clarified very soon. Okay, in example, but this is the definition there. And requirement 3 is the most complicated one. Is what they call base rule. Okay. So at this message, okay, and what is believed of this type, okay, will be looking at all possible type. It send a message, right? It's proportional to that, right? It's proportional. Okay, so that is a base rule. This is a standard base rule idea, right? You look at all the possible type that send a message, right? And proportional to that belief. Okay. This belief is common or prior. So looks complicated, but let's look at the example, then you see all this definition makes sense. I mean, you look at this abstract thing, I don't think you will understand unless you are a very math person. Look at the example, and then I will look at the numerical example, then you will see how these things being understood. Okay. So usually you will see in the literature, they will usually look at two equilibrium outcome, two classes of equilibria, and there's a third one. But you will see the third one is a mixture of the first two. The first one is very simple. The different type of senders, right? So you say different senders and different signals separate. Okay. And pooling means all types are the same. Okay. And hybrid means that they're mixing, right? There's some mixing, there's some pooling, right? Maybe the first two types send the same signal, right? The last type send different one, send a different one. But usually we focus on separating or pooling, because that would be only two types, right? So you don't have to worry too much about hybrid. If you don't allow them to do probabilistic mixed strategy, okay? If you do pure strategy, then it's likely that this is only the first two is only a case you consider. So we'll ignore the hybrid. We only do the separating and pooling. Okay. So this example here make our analysis very transparent. Okay. And nature will decide half the time is up or down, type 1, type 2. Okay. And the sender choose left or right. Okay. And the receiver choose up or down. Okay. And do note that receiver only choose action based on message. So you choose up here, it must be up here. And down must be, if down here, down there. Okay. So do note that the receiver only have two-dimensional strategy. Up on seeing left, up or down. Up on seeing right, up or down. Okay, not for only two. Okay? Because only two information set here. Okay, and the sender also have two-dimensional strategy. You have to say if he is type 1, left or right. If he's a type 2, left or right. So it's 2 by 2. Okay? So everyone have 4. Okay, but do note that the one more complication here is mainly the receiver have to assign probability here or here, and here and here. Okay, must be probability, so must add to 1. Now we solve the game. So look at this. Okay, we try to argue that this is separating equilibrium. Okay, let's see the check. Okay, now let's check it. So how do we solve this kind of signaling game? Is you have to check all possible scenarios, same as what we do next equilibrium. So first is we focus on the case separating, means that sender must be choosing one strategy here and one strategy here, because we focus on pure strategy. So they're separated means they're different. So it must be the case either LR or RL, right? Otherwise it's called pooling, right? So they send different signal. Now, first is we would impose immediately the base rule, okay? Because if this equilibrium, the second step will be this must be 1, right? The other must be 0, right? That is something that we require, right? The base rule is the belief must be derived from the actions, right, on the equilibrium path. Okay. equilibrium will appear here, right? Because if you play this game many times, half of the time you see L, half time you see right? And then you know that if left must be the upper guy, the right will be the lower guy, right? So you believe this is the case, okay? And if you are the receiver, if you see left, you know you are here, right? Then he's choosing either 3 or 0. It must be the case this is being chosen, right? And if you are the receiver, you know you're here, you look at 2 or 0, you must be doing down, right? So it must be this case, right? This is optimal for the receiver. Okay. What is left unchecked is the sequential representative sender, right? Because we assume what sender is doing right now. We don't check sender, right? The receiver is optimal, sender is optimal. Holding what receiver is doing. Will sender do this? Okay. If sender say, okay, I'm upper guy, am I be happier? I send R, okay, instead of L. If I send R, what I get is D, right? D, because he doesn't know, right? Suppose I deviate, I do D, I do R, then I'll face D, which gets 0, right? And compare 0 to 1, no deviation. Fine. Okay. So look at the second guy now. If you lower guy, lower sender. Currently you send R, which get payoff of 1. Now if you deviate, you go to L, your payoff become 2. So there's no way the sender will do this, still will go to L, right? If this is equilibrium, it can't be true because this guy would go to here. So there is no separate equilibrium to start with this one. Okay, that's how I said no equilibrium for this one. Is that okay? Is that okay? Now we are going to the other one, other case. We impose the condition where sender send R, receiver send L. Right? So this is our assumption. We'll check at the end, of course. This is our assumption here. If this is the case, we play this game many times. We have 1 here, 1 here, right? This is following the first condition. Base rule have to be observed according to the play of the game. And if you expect to be 1 here, what happened is what happened to the player 2, the receiver? If he believes it's here, he's choosing between 1 or 0. He will do that up, right? And if the receiver believes he's here, he's comparing 4 and 1. He will do up as well. So now we have rational for sender. Now, sorry, receiver. So we have to see whether the sender actually willing to do this. Check. If your sender up guy, if you follow the equilibrium, what you get? You get 2 here. Okay. If you deviate, if you send L instead, you get 1. So that's okay. That's done. Look at your bottom sender. In equilibrium, you're getting 2. All right. If you deviate, you get 1. So you don't. So this is a subgame perfect Bayesian equilibrium, right? Because no player want to deviate. The belief is derived nicely, right? It's follow the Bayes theorem, and this is a belief assigned in every information set. That's done. Okay, so everything is all right. So basically, you can see solve this kind of game is same as Nash equilibrium, right? Just check everything, no one deviate, right? So it's not something too complicated. Now we're going to have more fun because so far the assignment of belief is so easy, right? It just now we have more complicated one. Okay. Now we consider a case where both sender is going to send left. Okay. If both sender are going to send left in equilibrium, what do you think you see left? You learn nothing, right? Because both types send left means that, well, they're the same, right? So you can't see what's going on, right? So same, right? So it's remaining the same. That nothing can be learned there, okay? And now the question is, what happened to the receiver? What should be done? The receiver have to say half of the time, if he choose U, half of the time is 3, half time is 4. So the payoff is 3.5. Half of 0, half of 1, the payoff is 0.5. Right? So U is the thing is better. Now here comes the challenge to the receiver on the other side. Right? The receiver actually said, okay, I see out. What should be the belief? It's never happened. So there's nothing restrict in our equilibrium. What should be the Q? Q can be anything. So what can we do? Q can be anything. So what should be done is we have to make sure that the receiver choice have to make that the sender don't want to do otherwise. Okay. So let's see the following. Let's try one by one. Okay. Suppose, okay, the receiver, okay, choose the two choices, either up or down. So let's try up first. Okay. If it try up, okay, we have to find the belief that justify this thing. Okay, there's no restriction. And you can see up, the payoff is 1 times Q plus 0 times minus Q. So it's Q. Right? And if you choose down, the payoff is Q times 0, 1 minus Q times 2. So as long as Q is big enough, which is 2/3, you can check, you choose up. Right? If Q is less than 2/3, you choose down. Right? So that's fine, we know that. Now is no, is you believe you're here, then you choose up, right? You're here, you choose down. Right? The cutoff is 2/3. Now let's see if this is equilibrium. Okay. Well, as I said, we check already, it's optimal for the receiver already. So just check the sender. Is sender happy here? Sender 1. If you choose keep L, you get payoff of 1. Right? Right? But if you deviate, you get 2. So this can't be equilibrium. Right? So now let's check the other case. Is if we do not choose this, right? If instead we do that, right? Of course, Q has to be less than, right? If you choose D, it must be this case. Is this still equilibrium? Okay. And if the sender, upper sender, choose L, which give payoff 1, right? If you deviate, it will be 0, no deviation. Look at the sender here. He do the left will be 2, and do the right will be 1. So this is equilibrium. So there will be pulling equilibrium that this would happen, right? The receiver would choose down, that would be that, right? So that I think I have that in the next slide. Okay, it's actually here, right? It's actually this one, right? So this is the equilibrium, right? Where as long as your belief that is less than 2/3, right? You choose D, right? And there will be a continuum equilibrium, right? As long as you set the belief is less than 2/3. So there will be more than one equilibrium, the many equilibrium, as many as you want, because Q is unrestricted. Okay? Q can be 0, Q can be 1/2, Q can be 0.1, anything is fine. Okay? But doesn't really matter anyway, because this Q is not, as long as it's justifiable, this is the case, which we can justify, that's fine. Okay? Now, if that's okay, then we see the other one. Is it possible that both senders will send R? Right? So is it okay to see this happen? Okay. And as we have seen, if both are out, we have half and half, right? Because half of time should be up, half of time will be low, because the Bayesian will update, right? And if you're player 2, you are comparing 0.5 over 1, right? Because you choose up, half of time is here, half of time there is 0.5. If you choose down, half of 0, half of 2, that's 1. So D is the one that you're looking at, right? Now, the next part will be, okay, what about L? Okay, L, okay, is it going to be what we can assign? Okay. Now let's focus on this one. Okay, you can see if your player 2, right, up is 3 and 4, down is 0 and 1, right? It must be, no matter what P you are doing, right? Up is dominant, right? Because no matter you think where you are, whatever your P is, it must be up, right? I mean, no matter what you think, right? And no matter what P is, doesn't really matter, right? So it must be up. Okay? You can assign any P, doesn't really matter. Now the question now is optimal for receiver, optimal for sender. Sender, upper guy, okay? Upper sender is looking at payoff of 0. Okay? If no matter he deviate, no matter what, he's better. Right? No matter, actually doesn't really matter what he's choosing. Right? So he would just deviate. So it can't be the case. Done. There's no pool equilibrium in this one. Is that clear? Okay, so we're done. So you can see this kind of game is like, oh, it's complicated, right? It's complicated. It's not something easy, right? Because you look at all the possible things, it takes some time. But I hope that it's clear what do you mean by base rule, what do you mean by belief, right? How to update, right? And because this is a pure strategy, Nash equilibrium means that we exhaust every possibility when we talk about pure strategy, right? But of course, you can allow the sender randomize over this, right? And then you have a hybrid equilibrium, which I'm not going to take into account, but you can easily do all these things as well, right? But of course, when you have mixed strategy, right, then you have to make strategy here, right? Then you have to look at the probability according to the outcome, right? So, but that would be something that beyond the scope of we are covering, but you can actually do it. Is that okay? Now, only remaining time. I don't want to go into the new model, but I want to give you the background of this model. We talk about this later, but this is a very famous game by Spence. So people talk about Spence signaling game. Before, we just have a simple example, and we have a very interesting case here is what we are doing, economics or Ph.D. Basically, Spence said it's useless. Okay, even it's useless, it's still very useful. In what sense? Is you want to send a signal to show you are better. Okay, even though education is useless, it's good that you won't have to have a separating equilibrium. Okay, and that's what happened to peacock in the nature. No peacock, 孔雀, right? Male peacock. Okay, you notice almost every animal in the world, right, is the female looks more beautiful than the male, right? And peacock is probably one of the few animals that's reversed, right? The beautiful peacock you see is not the female, it's the male, right? And why is the case? And then it turns out that is the peacock, right? The more beautiful they are, actually is not conducive to their survival, right? Actually, the much more beautiful, much more elegant one actually is more likely to die, right? But why they do that is because they're strong. They show that they're very strong, right? By showing that even with these complicated feathers and looks nice, then they are doing good, right? So that is how you want to distinguish yourself from others, right? By saying signal, right? And then that is the idea why we do PhD. Why spend 5 years in a school and doing something nonsense, right? I mean, maybe some of you doing very important job, right? But I guess as D.O.T.E. said, right, 90% of research is rubbish, right? Why we're doing rubbish, right? Why produce something no one ever read? I mean, unfortunately, right? You look at paper being published, the median publication by PhD is 0. So means that at least 50% of us is not going to publish any paper in any journal, okay, including rubbish journal, okay, crappy journal, right? No one publish anything, right? So you publish, then there's no one see it, right? Why do it? It's because doing PhD is tough, right? Not everyone can do it. You want to show your ability by doing something crazy, and you can distinguish from others, right? And that's a question, right? Why women like flower? Right? Flower is almost a crab, right? Just after 10 seconds, or you just throw in the rubbish bin, right? Many of them get the flower, maybe in the Valentine's Day, you get 1,000 rose. And after 10 seconds, you feel a touch, you cry a little bit and put it in the 朋友圈 and 小红书, and then just throw in the rubbish bin, right? Just 10 seconds. Why you do that? Why you care? Why you care about that, right? Complete rubbish, right? But say signaling, right? Signaling is just showing that, okay, why you care about it? Why you touch about it? Because it's no practical use, but it shows that the boy is willing to spend nonsense amount on you, right? It's so that this is important, right? It's not you care about the rose. You never put 1,000 rose in your room. There's no use, right? After one, at most 1 day, you just throw in the rubbish bin, right? Why? Why they care about that? But that's because of signaling, right? Because not everyone can do it, right? By showing this is very important, right? It's showing that you get education, right? You get something very troublesome is very important. The sort of signal, right? That's not make a difference. By willing to do it, it's very important. Okay, you can separate those who good and those who are bad. All right, just like we have qualifying exam for a PhD, right? Do you think the qualifying exam is going to tell us who is going to do better research or not? Definitely not, right? But we're able to tell who is better, who is worse, right? And then we keep the better one more likely than keep it, right? Because everyone can apply for PhD, claim that he is happy to do research, right? But doing research requires a lot of persistence, right? A lot of hard working, right? So by making the course very hard, okay, then can screen you out, right? Keep the best candidate, right? So that's the idea, okay? So we're trying to show you that education is signal, right? Although it doesn't improve productivity, by asking people to show the education, I only left with good candidate, right? So now these days, you know, right? That's why these days, right, when you look at people, high janitor, right, require college degree. Why? I mean, that is the reason, right? Why you would hire a security guard that has to know English? That's the idea, right? So let's see the game, and then we would defer the analysis in the next class. Okay. So the game is like this, very simple, as we have seen, right? So that nature decide high type, low type, right? Same as this one. Nature decide worker is good or bad with some probability. Okay. And now high type and low type will decide how much education he's going to get, right? And education is costly, okay? And we have assumed that, okay, higher type is less costly than the low type because this is first derivative, right? To extra education for the high type is lower than the marginal cost for the low type, okay? If you're better, if you're smart, okay, another year in the school doesn't make too bad, right? That's why it's sojourn in the US PhD. Now before it's like 4 years, the beginning is 4 years. Now it's when I graduated the time 10 years ago, 10 years ago, yeah, 10 years ago, it's like 5 years. And then now it's like 6 years. And very soon will become 7 years because you need a postdoc now. And now before you put PhD, you get a pre-doc. So you have 2 years before in the US, right? And then you have 6 years in the middle, another 3 years in postdoc. So like how many years you get? 6 plus 3 is 9, 9 plus 2 is like 11, net 11 years, right? Company, I mean, most of the time is basically race, right? Anyway, well, but that's why the signaling, right? Signaling game. Because involution, right, is 卷起来. So here is the idea, okay? And we can actually allow education to be beneficial, okay? We can say, okay, actually it's not crucial to the model, okay? We say if you are doing 1 more year in school, actually you're more productive, okay? It's not crucial to the model, but just make it more realistic, right? Just less cynical. So if you are high type, right, your marginal product increase is more than the low type, okay? And this model is, will have, in the original model, you will have many firms, but 1 worker, okay? Because worker apply for many firms, right? Then he receive offer. So, but later you will see when we're competitive market, that reduced to 1 firm, 1 worker. But in the original model, it's a competitive market, okay? Because it's a 70s, right? There's no, in the market is the main thing. So that's why if there's take the highest offered, okay, but turn out that they will be the same, okay? And it's a Bertrand, the Bertrand idea. So everyone give the same offer anyway. Look at your education, this is my offer. So there's no, and your payoff depend on your wage, okay? Minus the cost of education, and the payoff will be the productivity minus the wage, right? So that is the model, okay? And then this is the end thing, because competition of worker, that's Bertrand of the firm, so which means that the profit of hiring a worker will be 0, okay? So that means that, okay, if the firm, okay, looking at the same education, okay, look at their PhD, right? Then they would think that they have same productivity, right? That means that the wage is given by expected productivity, okay? That means that even though in the model you have multiple firms, there will be no different the wage they offer, right? It's Bertrand competition. So that's why we reduce the model to multiple firm one worker as one firm, one worker. Because if two firms make different offer, the worker will take the best offer, right? So they undercut until the offer is same as the expected productivity. So that means that it become one-to-one game that we analyzed before. So we'll do that again next class. Then we will be prepared to have enough sleep for next class, because next class will be, I guess, is most complicated for our whole course. Okay, and then I'll upload the slide for the concept theory that we'll talk about this in the next class as well. I'll upload that. So I will see you next week. Enjoy. So have fun. I say I want to answer any question you have. I think I'll upload the assignment as well, but I haven't done it, but I'll upload the assignment as well today. So I will see you next week. Bye bye. Thank you. I say I want to answer any question you may have.